Hello everyone, welcome to the Biochemistry web channel. Within the scope of organic chemistry course, I'm here with the topic titled Matter and its Characteristics. Let's start. The contents of the topic are states of matter, which is the first major title, and the classification of matter, boiling, melting, and freezing points, energy and energy units, energy and phase changes, gases, solids, and liquids are explained under states of matter. And the second major title is interaction of light with matter, and emission, absorption, transmission, reflection, and spectroscopy are explained under interaction of light with matter. Let's start with states of matter. And as you see here, the figure tells something us about the characters of solid, liquid, gas, plasma. Solids are hard, fixed-shaped, and they have constant volume. When we look at the liquids, they are not hard, the shapes are variable, but they have constant volume. Gases, not hard, they have variable shape and volume. And the plasma, which is the fourth state of matter, when gaseous substances are energized, electrons can be detached from some gas atoms. And after a while, as you see in the picture, there is a mixture of free electrons and ions together with the neutral atoms. And this mixture is called plasma. Plasma is actually ionized gas. And examples are sun, lightning, thunderbolts, fluorescent lamps, and also the plasma TVs. And from solid to liquid and gas and plasma, the energy increases. Matter exists in four states: gas, liquid, solid, and plasma. Why are some molecular compounds solid at room temperature, others gas, and others liquid? And the answer is on the competing forces. Intermolecular forces work to hold particles together as liquid or solid. So the kinetic energy or motion or temperature also works to separate particles. The kinetic energy means also the temperature. The temperature increase in the temperature, increase the kinetic energy. A gas consists of particles that are far apart and move rapidly and independently from each other. A gas has no specific shape or volume. The particles of a gas expand to fill the volume and take the shape of the container in which they are placed. A solid consists of particles, atoms, molecules, or ions that are close to each other and are often highly organized. Particles in a solid have little freedom of movement and are held together by attractive forces. They are characterized by a regular organization. A solid has a definite volume and retains its shape independently of the container in which it is placed. A liquid consists of particles that are much closer together but are still somewhat disorganized since they can move about. Particles in a liquid are close enough to each other to exert an attractive force. A liquid has a definite volume but takes the shape of the container in which it is contained. A plasma is a hot ionized gas consisting of approximately equal numbers of positively charged ions and negatively charged electrons. A plasma has no specific shape or volume. Unlike gases, plasmas are electrically conductive, generate magnetic fields and electric currents, and respond strongly to electromagnetic forces. And here in this picture, you see three examples of three different states of matter, as in the atmosphere, the nitrogen and the oxygen gases. the water, the seawater, which is liquid water, and solid silic silica dioxide, which is the component of sand. And also here you see the three states of water. A molecule with solid water, which the particles of a solid are close together and highly disorganized. In the liquid water, the particles of a liquid are close together but more disorganized compared to the solid water. And the particles of a gas are far apart and disorganized. So you can easily consider the molecular pattern or the attractive forces exert on three different states of water. So highly organized, disorganized, more disorganized. Whether a substance exists as a gas, liquid, or solid depends on the balance between the kinetic energy of its particles and the strength of the interactions between the particles. In a gas, the kinetic energy of motion is high, and the particles are far apart from each other. As a result, the attractive forces between the molecules are negligible, and gas molecules move freely. In a liquid, the attractive forces hold the molecules much more closely together, so the distance between molecules and the kinetic energy is much less than the gas. In a solid, the attractive forces between molecules are even stronger, so the distance between individual particles is small and there is little freedom of motion. If you want to remember your knowledge about the attractive forces, which means intermolecular forces, you can check general chemistry lecture or general chemistry video, which is the first topic of organic chemistry. Classification of matter. All matter can be classified as either a pure substance or a mixture. A pure substance is composed of a single component and has a constant composition, regardless of the sample size and the origin of the sample. A pure substance cannot be broken down to the other pure substances by any physical change. The chemical compositions of pure substances are a substance constant that can be employed in the characterization of matter. The uncomplicated compositions of pure substances dictate straightforward physical attributes, such as boiling point, freezing point, etc. Pure substances play a significant role in various fields, including the pharmaceutical industry, scientific researches, and the foundational framework of semiconductor technology, which underpins the production of computer chips. A mixture is composed of more than one component. The composition of a mixture can vary depending on the sample. A mixture can be separated into its components by physical changes. Dissolving a table sugar in water forms a mixture, whose sweetness depends on the amount of sugar added. If water is allowed to evaporate from the mixture, pure table sugar and pure water are obtained. Mixtures can be formed from solids, liquids, and gases. Along with the content of mixtures, there are changes in many of their properties, such as density, appearance, freezing, and boiling points. In this image, you see sugar and water as pure substances, and one is solid and the other is liquid. Solid sugar, liquid water. And when we add sugar to water, we get sugar water, which is a mixture. A pure substance is classified as either an element or a compound. An element is a pure substance that cannot be broken down into simpler substances by a chemical reaction. A compound is a pure substance formed by chemically combining two or more elements. Nitrogen gas, aluminum foil, and copper wire are all elements. Water is a compound because it is composed of the elements hydrogen and oxygen. In this picture, you see the aluminum as an element, nitrogen as an element, water as a compound, and sodium chloride as a compound. And here you see a good diagram showing the classification of matter. So anything with mass and volume we call matter. If matter contains more than one component, it's a mixture. A single component, it's a pure substance. If a pure substance cannot be broken down into simpler substances, it is an element. If a substance composed of two or more elements, it's a compound. Boiling, melting, and freezing points. Ionic compounds are composed of extensive arrays of oppositely charged ions that are held together by strong electrostatic interaction. And these ionic interactions are much stronger than the forces between covalent molecules. So a large amount of energy is required to pull the ions apart. These ionic interactions are much stronger than the forces between covalent molecules. So it takes a great deal of energy to separate ions from each. Intermolecular forces are the attractive forces that exist between molecules. There are three different types of intermolecular forces in covalent molecules, which they are hydrogen bonding, van der Waals forces, including London dispersion force, and dipole-dipole interactions. And the strength of the intermolecular forces determines whether a compound has a high or low boiling point and melting point. In covalent compounds, the nature and the strength of the attraction between individual molecules depend on the identity of the atoms. So if you don't remember the intermolecular forces, please check topic 1, general chemistry. London dispersion forces are very weak interactions due to the momentary changes in electron density in a molecule. All covalent compounds exhibit London dispersion forces. The larger the molecule, the larger the attractive force between two molecules, and the stronger the intermolecular forces. Dipole-dipole interactions are the attractive forces between the permanent dipoles of two polar molecules, and hydrogen bonding occurs when a hydrogen atom bonded to oxygen, nitrogen, or fluorine is electrostatically attached to an oxygen, nitrogen, or fluorine atom in another molecule. The boiling point BP of a compound is the temperature at which a liquid is converted to the gas phase, while the melting point MP is the temperature at which a solid is converted to the liquid phase. When a liquid is heated, it eventually reaches a temperature at which the vapor pressure is large enough that bubbles form inside the body of the liquid. This temperature is called the boiling point. Once the liquid starts to boil, the temperature remains constant until all of the liquid has been converted to gas. Liquids boil when their vapor pressure is equal to the pressure exerted on the liquid by its surroundings. The strength of the intermolecular forces determines the boiling point and melting point of compounds. The stronger the intermolecular forces, the higher the boiling point and melting point. The freezing point of a liquid is the temperature at which the liquid and solid phases are in equilibrium under atmospheric pressure. As a liquid is cooled, its particles lose kinetic energy, and through the forces of attraction, they begin to solidify by losing energy to a level suitable for being fixed within a crystalline lattice. In theory, the melting point of a solid should be the same as the freezing point of the liquid. In practice, small differences between these quantities can be observed. And here you see the methane, which is the component of natural gas, and water. Both are small molecules with hydrogen atoms bonded to a second row element. So you might expect them to have similar melting points and boiling points. However, look at the methane, however, is a non-polar molecule. As you see, there is no any lone pair which contribute to the polarity, exhibits only London dispersion forces, whereas water is a polar molecule, can form intermolecular hydrogen bonds. As a result, the melting point and boiling point of water are much higher than those of methane. Look at the boiling point of water, 100 degrees Celsius. And what about the boiling point of methane? Minus 162 degrees Celsius. In fact, the hydrogen bonds in water are so strong that it's a liquid at room temperature, whereas methane is a gas. In comparing two compounds with similar types of intermolecular forces, the larger compound generally has more surface area and therefore a large force of attraction, giving it a higher boiling point and melting point. Energy and units of energy. As a simple definition, energy is the capacity to do work, and the potential energy is stored energy. Kinetic energy is the energy of motion. Energy can be converted from one form to another, which is the one rule. The law of conservation of energy governs the process. This is the first law of thermodynamics. Total energy in a system does not change. Energy cannot be created or destroyed. And we will deal with the topic of energy in more depth in thermodynamics. What are the units of energy? Energy can be measured using two different units, calories, cal, and joules, J. A calorie is the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. And joules and calories are related. And 1 calorie equals to 4.184 joules. Since both the calorie and the joule are small units of measurement, more often energy in reactions are reported with kilocalories or kilojoules. And 1 kilocalorie equals 1,000 calorie, 1 kilojoule equals 1,000 joule, thus 1 kilocalorie equals 4.184 kilojoule. And here I want to mention that the calorie is the thermodynamic calorie. When an organism eats food, the protein, carbohydrates, and lipids are metabolized to form small molecules that in turn are used to prepare new molecules that cells need for maintenance and growth. This process also generates the energy needed for the organs to function, such as allowing the heart to beat, the lungs to breathe, and the brain to think. The amount of stored energy in food is measured using nutritional calories. And the uppercase C instead of small letter c is used. And let's get the relation between nutritional calories and the thermodynamical calories. And one nutritional calorie equals to 1,000 calorie, thermodynamic calorie. For example, 1 gram of protein or 1 gram of carbohydrate typically releases about 4 nutritional calories per gram, while fat releases 9 nutritional calories per gram. If you know the amount of each of these substances contained in a food product, we can make a first approximation of the number of calories it contains by using the caloric values as conversion factors. The dietary calorie is an energy unit commonly used to describe the energy contents of food. And physical unit calorie is the energy required to increase the temperature of 1 gram of water by 1 degree Celsius. And the dietary calorie is a kilocalorie, the thermodynamic calorie. The dietary calorie would then raise the temperature of a 1 kilogram of water by 1 degree Celsius. It is common practice to just use the unit kilocalorie to avoid the confusion between the thermodynamic calorie and the nutritional calorie. When an individual eats more calories than are needed for normal body maintenance, the body stores the excess as fat. The average body fat content for men and women is about 20% and 25% respectively. This stored fat can fill the body's energy needs for 2 or 3 months. Frequent ingestion of a large excess of calories results in a great deal of stored fat, causing an individual to be overweight. When energy is absorbed, a process is said to be endothermic. When energy is released, a process is said to be exothermic. In a phase change, the physical state of a substance is altered without changing its composition. Now it's time to look phase changes. And in each phase change, I also mention whether that change is endothermic or exothermic. Converting a solid to a liquid. Converting a solid to a liquid is called melting. Melting is an endothermic process. Melting is an endothermic process. Melting is a phase change because the highly organized water molecules in the solid phase become more disorganized in the liquid phase, but the chemical bonds do not change. Each water molecule is composed of two oxygen-hydrogen bonds in both the solid and the liquid phases. Energy must be absorbed to overcome some of the attractive forces that hold the organized solid molecules together to form the more random liquid phase. And the amount of energy needed to melt 1 gram of a substance is called its heat of fusion. Heat of fusion, and the unit is calorie per gram. Freezing is the opposite of melting. Freezing converts a liquid to a solid. Freezing is an exothermic process because energy is released as the faster moving liquid molecules form an organized solid in which particles have little freedom of motion. And here in the picture you see the ice water and liquid form water from ice to liquid. We call it melting and endothermic process. And to absorb energy as an essential thing which provide overcoming of attractive forces. An exothermic reaction, the freezing is exothermic, converting liquid water to ice, less organized to high organized form. Converting a liquid to a gas. Converting a liquid to a gas is called vaporization. It's an endothermic process. Condensation is the opposite of vaporization. Condensation converts a gas to a liquid. It's an exothermic process. And here you see the liquid water and the gas water in the steam. This is converting liquid to gas. We call it vaporization and the endothermic process. And energy must be absorbed to overcome the attractive intermolecular forces of the liquid phase to form the gas molecules. And the amount of energy needed to vaporize 1 gram of a substance is called its heat of vaporization. A high heat of vaporization means that a substance absorbs a great deal of energy as it is converted from a liquid to a gas. Water has a high heat of vaporization. As a result, the evaporation of sweet form the skin is a very effective cooling mechanism for the body. Vapor pressure or equilibrium vapor pressure is defined as the pressure exerted by a vapor in thermodynamic equilibrium with its condensed phase, solid or liquid, at a given temperature in a closed system. And the inverse way, which is an exothermic reaction, which I call the condensation, in exothermic reaction, energy is released as the faster moving gas molecules form the more organized liquid phase. Converting a solid to a gas. Occasionally, a solid phase forms a gas phase without passing through the liquid state. This process is called sublimation. The reverse process, conversion of a gas directly to a solid, is called deposition. Carbon dioxide is called dry ice because solid carbon dioxide sublime to gaseous carbon dioxide without forming liquid carbon dioxide, and this is called sublimation. It's an endothermic process. And the inverse is exothermic, and we call it deposition. Carbon dioxide is a good example of a solid that undergoes this process at atmospheric pressure. At reduced pressure, other substances sublime. For example, freeze-dried foods are prepared by subliming water from a food product at low pressure. And here a good figure summarizing the phase changes. And also, I think this figure makes easy to study the phase changes. Here you see the solid, liquid, and gas. It's a triangle. And the first phase change is sublimation, converting a solid to a gas. And converting a gas to a solid is deposition. Sublimation is an endothermic process. Deposition is an exothermic process. Converting a gas to liquid is condensation and an exothermic process. Converting a liquid to gas is vaporization and an endothermic process. Converting a solid to a liquid is melting, and then melting is endothermic process. Liquid to solid is freezing, and an exothermic process. And also here I will draw the plasma, the fourth state of matter. So converting a gas to plasma, it is called ionization. Ionization. And it's an endothermic process. Converting a plasma to gas state is called deionization. And it's an exothermic process. Anyone who has ridden a bike against the wind knows that even though we can't see the gas molecules of the air, we can feel them as we move through them. Air is a mixture of gases, 78% of nitrogen, 21% oxygen, and 1% other gases, including carbon dioxide, argon, water, and ozone. Simple gases in the atmosphere, oxygen, carbon dioxide, and ozone, are vital to life. Oxygen, which constitutes 21% of the Earth's atmosphere, is needed for metabolic processes that convert carbohydrates to energy. Green plants use carbon dioxide, a minor component of the atmosphere, to store the energy of the sun in the bonds of carbohydrate molecules during photosynthesis. Ozone forms a protective shield in the upper atmosphere to filter out harmful radiation from the sun, thus keeping it from the surface of the Earth. And now it's time to start gases, to tell something about gases. A gas consists of particles, atoms, or molecules that move randomly and rapidly. The size of gas particles is small compared to the space between the particles. Because the space between gas particles is large, gas particles exert no attractive forces on each other. The kinetic energy of gas particle increases with increasing temperature. When gas particles collide with each other, they rebound and travel in new directions. When gas particles collide with the walls of a container, they exert a pressure. Pressure is the force exerted per unit area. That's pressure equals force divided area. All of the gases in the atmosphere collectively exert atmospheric pressure on the surface of the Earth. The value of the atmospheric pressure varies with location, decreasing with increasing altitude. Atmospheric pressure also varies slightly from day to day, depending on the weather. Atmospheric pressure is measured with a barometer. A barometer consists of a column of mercury sealed at one end and inverted in a dish of mercury. Many different units are used for pressure. The two most common units are the atmosphere, ATM, and the millimeters of mercury, where 1 atmosphere equals 760 millimeter mercury. And 1 millimeter of mercury is also called 1 torr. 1 torr. In the United States, the common pressure unit is pounds per square inch, and where 1 atmosphere equals 14.7 pounds per square inch. Pressure can also be measured in pascals, which 1 millimeter mercury equals 133.232 pascals. The molar volume of a gas expresses the volume occupied by 1 mole of that respective gas under certain temperature and pressure conditions. The most common example is the molar volume of a gas at standard temperature and pressure, which is equals to 22.4 liters for 1 mole of any ideal gas at a temperature equal to 273.15 Kelvin and the pressure equal to 1.00 atmosphere. Taking a patient's blood pressure is an important part of most physical examinations. Blood pressure measures the pressure in an artery of the upper arm using a device called sphygmomanometer. A blood pressure reading consists of two numbers such as 120 per AT, where both values represents pressure in millimeter mercury. The high number, such as 120, is the systolic pressure and refers to the maximum pressure in the artery right after the heart contracts. The lower number here, it is 80, is the diastolic pressure and represents the minimum pressure when the heart muscle relaxes. A desirable systolic pressure is in the range of 100 to 120 millimeter mercury. The desirable diastolic pressure is in the range of 60 to 80 millimeter mercury. There is an ideal gas, which is composed of point masses and lacks volume. And ideal gases infinitely dilutable. No interactions occur between gas particles. In real, an ideal gas is a theoretical gas composed of many randomly moving point particles that are not subject to interparticle interactions. Since it is difficult to precisely define a real gas, people have derived the definition of an ideal gas as an approach to help us model and predict the behavior of real gases. Ideal gases do not attract or repel each other. Ideal gas molecules themselves take up no volume. There is no absolutely ideal gas, but there are many gases that are close to ideal, making the concept of an ideal gas very useful in many situations. In fact, gases at room temperatures close to room temperature, and pressures close to atmospheric pressure. Most gases of interest to us are very close to being ideal. Real gases occupy space, and particles interact with each other. They only attain their properties in a very dilute state, and therefore the general laws apply to ideal gases. In other words, the ideal gas approach can be used with reasonable accuracy. Real gases approach the ideal gas at high temperature and low pressure. Ideal gases move away from the ideal at low temperature and high pressure. Gases with small molar mass and low polarity are the gases closest to the ideal, such as hydrogen gas. Four variables are important in discussing the behavior of gases: pressure, volume, temperature, and number of moles. And here the temperature is not the Celsius, it is Kelvin temperature or thermodynamic temperature. The relationship of these variables is described by equations called gas laws that explain and predict the behavior of all gases as conditions change. Three gas laws illustrate the interrelationship of pressure, volume, and the temperature. And these are Boyle's law or Boyle-Mariotte law relates pressure and volume, Charles' law relates volume and temperature, Gay-Lussac's law relates pressure and temperature. Boyle's law: for a fixed amount of gas at constant temperature, the pressure and volume of a gas are inversely related. And here you see in the animation, when the pressure increases, the volume decreases. Also follow the pressure gauge here and the volume indicators. So as a result, pressure times volume always give a constant number when we compare the initial phase, end phase, or any phase in the process. And also this provides us the equation P1V1 equals P2V2, which this represents the initial phase and this is the last phase. A balloon is a good example of Boyle's law in action. The balloon is inflated by blowing air into it. The pressure of the air pulls on the rubber, causing the balloon to expand. When one end of the balloon is compressed, the pressure within rises, causing the unsqueezed section of the balloon to expand outward. During respiration, our lungs make use of Boyle's law. While inhaling, the lungs are filled with air, therefore they expand. The volume increases as the pressure level goes down. Similarly, when the lungs are evacuated of air, they shrink. Therefore, the volume reduces and the pressure increases. The change in pressure and volume is momentary and periodic in nature. Continue on Charles' law. All gases expand when they are heated and narrows when they are cooled. For a fixed amount of gas at constant pressure, the volume of a gas is proportional to its Kelvin temperature. Volume and temperature are proportional. That is, as one quantity increases, the other increases as well. Thus, dividing volume by temperature is a constant. And as you see in the animation, it's clear that when the temperature increases, the volume increases. And follow the temperature here, the Kelvin temperature I mean, and what happens if temperature increases in the volume indicator. Increasing the temperature increases the kinetic energy of gas particles and they move faster and spread out, thus occupying a large volume. If you get the chance to read the instructions on a bottle of deodorant, you might have read the warning signs indicating the bottle to be kept away from the sunlight and high temperature. The answer lies in Charles' law. Under high temperatures, the air molecules inside the bottle will expand, which can lead to the bursting of the deodorant bottle. Most of you might have observed that the basketball, when left outside on a cold winter night, shrinks in size. As the temperature decreases, so do the volume of the gas inside the basketball. This forms the example that a constant pressure, a decrease in temperature will lead to a decrease in volume. However, the basketball gains its volume back when the environment is changed, such as you bring it in a warm room. Charles' law finds its way into our kitchens as well. In case you have ever tried your hand at baking, you might be familiar with the substance most commonly used in cooking, the yeast. Yeast is often used in baking to make the bakery products fluffy. Yeast is responsible for releasing carbon dioxide bubbles. These carbon dioxide bubbles expand further with high temperature. The expansion of the carbon dioxide bubbles with an increase in temperature works as a leavening agent and causes the bakery products to become fluffy. And here the equation, the initial phase V1 divided T1 equals V2 divided T2, that's the end phase. Gay-Lussac's law. This law describes how the pressure of a gas changes as the Kelvin temperature is changed. For a fixed amount of gas at constant volume, the pressure of a gas is proportional to its Kelvin temperature. That is, as one quantity increases, the other increases. Thus, dividing the pressure by the temperature is a constant K. Increasing the temperature increases the kinetic energy of the gas particles, and if the volume is kept constant, the pressure exerted by the particles increases. And we have the equation explaining the initial phase and the last phase, P1 divided T1 and P2 divided T2. Think about the cookers, the pressure cookers, which are sealed utensils for cooking food under steam pressure. It is usually made up of steel or aluminum. When heat is applied, the water inside the cooker vaporizes and the steam is produced. The steam is periodically released through a valve to maintain the operating pressure inside the cooker. Pressure cooker, if the valve of the pressure cooker malfunctions and the heat flow is not interrupted, the pressure inside the cooker escalates. The increase in the pressure is due to Gay-Lussac's law, such as the pressure of a fixed amount of a gas increases with its temperature at constant volume. And this high pressure may rupture the cooker and may lead to an unfortunate accident. Another example is, in hot summer days, the inflated tires of vehicles may burst. The bursting of tires is caused by Gay-Lussac's law. The inflated tires are under high pressure. When the temperature of the air rises, the pressure of the gas in the tubes increases, and after an unbearable point, the tires fracture. And here, the combined gas law welcomes you. All three gas laws, Boyle's, Charles, and Gay-Lussac's laws, can be combined in a single equation, the combined gas law, that relates pressure, volume, and temperature. And this is the equation, P1 times V2 divided T1 equals to P2 times V2 divided T2. And the fourth law is the Avogadro's law. Avogadro's law describes the relationship between the number of moles of a gas and its volume. When the pressure and temperature are held constant, the volume of a gas is proportional to the number of moles present. Thus, as the number of moles of a gas increases, its volume increases. Thus, dividing the volume by the number of moles is a constant. And the value of constant is the same regardless of the identity of the gas. Thus, if the pressure and temperature of a system are held constant, increasing the number of moles increases the volume of gas. And here the equation V1 divided N1 equals V2 divided N2. All four properties of gases, pressure, volume, temperature, and number of moles, can be combined into a single equation called the ideal gas law. And the product of pressure and volume divided by the product of moles and Kelvin temperature is a constant, called the universal gas constant and symbolized by R. And here's the equation. P times V equals N times R times T, or as in the definition, the pressure and volume, the product of pressure times volume divided by the product of moles and Kelvin temperature is constant, which is R, the universal gas constant. And it's time for Dalton's law. It describes the relationship between the partial pressures of the components and the total pressure of a gas mixture. The total pressure, P total, of a gas mixture is the sum of the partial pressures of its component gases. Thus, if a mixture has three gases, A, B, and C, with partial pressures of pressure A, B, and C respectively, the total pressure of the system is the sum of the three partial pressures, as seen in the equation. Under normal conditions with non-metal elements, hydrogen, oxygen, nitrogen, chlorine, and fluorine, the noble gases such as helium and radioactive radon are in gaseous forms. Some covalent molecules such as ammonia, carbon monoxide, and hydrochloric acid are in gaseous forms. And we finish gases. It's time for solids. A solid is a comprised of closely packed and typically highly organized particles, atoms, molecules, or ions. The particles in a solid possess very limited degrees of freedom for movement and are held together by attractive forces that exhibit a regular arrangement. A solid has a definite volume and maintains its shape regardless of the container it is placed in. Solids can be classified based on whether or not the arrangement of this particle is ordered in or not. And ordered solids called crystalline, not ordered are amorphous solids. Amorphous solids, they have no regular repeating pattern of ions or molecules. An amorphous solid does not have a definite geometric or crystalline shape. Most classes of solid materials can be found or prepared in an amorphous form. Common window glass is an amorphous ceramic. Many polymers are amorphous. And even foods such as cotton and candy are amorphous solids. An amorphous solid is any non-crystalline solid in which the atoms and molecules are not organized in a definite lattice pattern. And glass, plastic, gel, and rubber is an example of amorphous solid. In crystalline solids, however, each ion or molecule has a fixed position within the lattice structure formed, and they are very difficult to deform and break quickly. And there are four types of crystalline solids, which one is the ionic, consists of oppositely charged ions held to one another by ionic bonds. Molecular crystallines consist of an ordered arrangement of molecules attracted to one another by non-covalent interactions. Covalent networks, atoms are held to one another by an arrangement of covalent bonds that extend through the solids. And the metallic crystalline solids, an array of metal cations immersed in a cloud of electrons that spans the entire crystalline structure. Let me to give more information about these crystallines. And the first one is ionic crystallines. The ionic crystallines consist of ions connected by ionic bondings, cations and anions. They conduct electricity in their solution or in liquid state, and they have a high melting point. And the examples are sodium chloride, potassium chloride, calcium sulfate, etc. Molecular crystallines are occurred by various non-covalent interactions. or intermolecular attractive forces. A molecular solid is composed of molecules held together mainly by van der Waals forces. Therefore, their melting and boiling points are low. And molecular solids can consist of monoatomic, diatomic, or polyatomic molecules. And the examples are dry ice or dry carbon dioxide, ice water, sugar, etc. And these are soft and usually have low melting points. They do not conduct electric current in liquid state or in their solutions. Covalent networks, also referred as atomic crystallines. So the atoms form the building blocks. They are connected by covalent bonds. They are rigid structures. There is no too many covalent network substances exist and their melting points are high. Metallic crystallines. It's a crystal structure made of metal ions and electrons with metallic bonds. And metallic crystallines have physical properties such as thermal and electrical conductivity and the brightness, such as sodium metal, magnesium metal, silver, and gold. Yes, it's time for liquids. A liquid is composed of particles that are much closer to each other, yet still somewhat disordered as they can move. The particles in a liquid are close enough to exert attractive forces on each other. The liquid has a definite volume, but takes the shape of the container it is in. There are some terms that we should define them regarding liquids, and the one is viscosity. Viscosity is the resistance to flow. It is related to the strength of the non-covalent interactions between the molecules that make up the liquid. The stronger the interactions, the thicker the liquid. Temperature has an effect on viscosity. Higher temperature produces lower viscosity. Liquids with large viscosity flow more slowly than those with small viscosity. For example, the flow of honey is slower than the flow of water because the viscosity of honey is greater than that of water. And the second parameter is density. Density is a density of a liquid or any other substance is the amount of mass contained in a given volume. And here's the equation explains this definition. Density equals mass divided by volume. Density is the relationship between the mass and the volume. In addition to this, we mentioned vapor pressure, boiling, and freezing points of matters in the previous slides. Cohesion and surface tension. Cohesion refers to the attraction of molecules for other molecules of the same kind, and water molecules have strong cohesive forces thanks to their ability to form hydrogen bonds with one another. Cohesive forces are responsible for surface tension, the tendency of a liquid surface to resist rupture and when placed under tension or stress. The cohesive forces between liquid molecules are responsible for the phenomena known as surface tension. The molecules at the surface do not have other like molecules on all sides of them, and consequently they cohere more strongly to those directly associated with them on the surface. This forms a surface film which makes it difficult to move an object from the surface than to move it when it's completely submerged. And examples are, for example, the insects walking on water, floating in needle. And also there are some substances which they decrease or increase the surface tension. And a good example for decreasing surface tension is the soaps, detergents, And bile acids, especially the bile acids, are so important for the digestion of lipids in gastrointestinal tract. Adhesion is the attraction of molecules of one kind for molecules of a different kind, and it can be quite strong for water, especially with other molecules bearing positive or negative charges. Adhesion enables water to climb upwards through thin capillary tubes placed in a beaker of water. This upward motion against gravity, known as the capillary action, which depends on the attraction between water molecules and the glass walls of the tube. This is adhesion, as well as the interactions between water molecules, cohesion. In this figure, you see a liquid placed in a container, and let's imagine that it is water. While the molecules in the water, inside the water, or inner part of the liquid, interact with each other in all directions, both cohesive and the attractive forces. But the molecules interact differently on the upper surface of the water that touches the air, and this creates the surface tension. Whether or not liquid molecules for the surface depends on the effect of two forces. These are the adhesion and cohesion, as I said. And so the forces of attraction between liquid molecules, and here the surface, for example, they come into contact with area called adhesion inside the cohesion, or the interaction between water molecules, cohesion, and the forces between the water molecules and the surface that they contact are called the adhesion forces. And the forces of attraction between the liquids of particles are called cohesion. If the adhesion forces are greater than the cohesion forces, the liquid spreads and wets the surface. When the cohesion forces are greater than the adhesion forces, the liquid drop retains its shape and does not wet the surface. And when the adhesion forces are greater than the cohesion, the liquid rises spontaneously in the capillary tube. And here a capillary tube. So the water uprise in the capillary tube when the adhesion forces are greater than the cohesive forces. The absorption of water by a paper napkin, towel, or sponge is related to the capillary effect. Another figure showing the interactions of water molecules in a liquid, explaining surface tension too. We have to understand the adhesive forces at work on surface tension. Water, for example, is a polar molecule that consists of a partial positive charge on the hydrogens and a partial negative charge on the oxygen. Thus, if in liquid water each molecule's partial positive charge is attracted to the neighbor's partial negative charge as seen here. This is the origin of the cohesive forces within water. Water molecules buried inside the liquid, is then being pulled and pushed evenly in every direction, producing no net pull. Meanwhile, the molecules on the surface of the liquid which interact with the air in the upward, lacking pulling forces in the upward direction, thus encompass a net downward pull. How does the cohesive force create a both concave up and concave down surface then? The answer is in its relationship with the adhesive forces between the water molecules and the container surface. When the cohesive force of the liquid is stronger than the adhesive force of the liquid concaves down in order to reduce contact with the surface of the wall as seen here. When the adhesive force of the liquid to the wall is stronger than the cohesive force of the liquid is more attracted to the wall, and then its neighbors causing the upward concavity. So meniscus concave up and down, which are related with the cohesive and adhesive forces. And this is the end of title 1 in the topic. Yes, the second major title of this topic is Interaction of Light with Matter. The interaction of light with matter can take many forms, such as emission, which matter releases energy as light; absorption, matter takes energy from light; transmission, matter allows light to pass; and reflection, matter repels light in another direction. Photons can be absorbed or emitted by matter, and photon energy matches jump in energy levels. Atoms absorb photon and gain energy. This gives rise to the absorption line spectrum of atoms and is characteristic. Atoms emit photons and lose energy. This gives rise to and is characteristic of the emission line spectrum of atoms. Under favorable conditions, ions, atoms, and molecules absorb energy when they encounter thermal, electrical, and radiation energy. In some cases, excited particles can react directly without additional energy. Molecules interact with rays. The energy received in the form of rays stimulates or enhances intramolecular oscillations. They can transfer electrons from a low energy orbital to a high energy orbital. Spectroscopy is a technique of splitting light into its constituent wavelengths, spectrum, in much the same way as a prism splits light into a rainbow of colors. In general, a spectrum is generally more than a simple rainbow of colors. The energy levels of electrons in atoms and molecules are quantized, and the absorption and emission of electromagnetic radiation only occurs at specific wavelengths. The frequencies of light emitted in such a case constitute the emission spectrum. When an electron comes down from an excited state to the ground state, it emits a photon of energy. And each photon has a specific wavelength, which is denoted by the lambda, Greek letter lambda. Electrons of an element which are in the ground state may absorb incident energy in order to reach a higher energy state. The frequencies of light transmitted through this substance, with dark bands showing absorbed light, constitute the absorption spectrum of the substance. If it energizes the electrons, they can jump to the higher energy levels. This is absorption. The electron takes energy and jumps to a higher energy level, but it is not stable. It returns after a while. On the way back from the upper level to the ground state, the electron gives off energy. This is emitted as light called photons. This is the emission. And the spectrum means the wavelengths of light absorbed or emitted by substances. So in emission spectra, if the rays emitted by an emitting substance are taken and the intensity of the emitted rays is measured at all wavelengths, the wavelengths at which the most intense rays are emitted are determined. In absorption spectra, if a substance is irradiated with continuously varying wavelengths and the intensity of the absorbed rays is measured, the wavelengths at which rays are absorbed by the substance and the characteristic absorption spectra can be determined. They are used in the characterization of substances and in the examination of their purity. Emission spectroscopy. In this method, the intensity of the rays emitted during the transition from the excited to the ground state is observed. So certain atoms, line spectrum, or molecules, broad fluorescent spectrum, emit absorbed rays at certain wavelengths. Absorption spectroscopy. Absorption occurs at wavelengths whose energy content can realize the excitation point position. The line spectra of alkalis are absorbed with a simple spectroscope and the absorption of light with spectrophotometers. And here you see the emission and the absorption spectrum of hydrogen, that's hydrogen line spectrum. The emission spectrum of a gas is represented by a collection of separated colored lines, as you see here, separated colored lines with dark spaces between them. The lines are the parts of the spectrum where emission occurs, thus photons are emitted, while the dark spaces are the parts where there is no emission, hence the darkness. The absorption spectrum of an element is represented by a continuous band of colors, as you see here, with separate dark lines between them. The entire band represents the total light that is focused on the element. The dark lines are the parts of the spectrum where the electrons absorb light photons. Hence, there is absence of light at these parts. Thus, these parts are emitted. In atomic physics, the Balmer series or Balmer lines are the 6 named series representing the emission spectral lines of the hydrogen atom. Most of the analytical methods in clinical biochemistry are based on spectral analysis. Actually, not on clinical biochemistry, in laboratory science in general. The intensity of the line of the emission spectrum is directly proportional to the number of excited particles. An example method here, flame photometer. The amount of light absorbed by atoms or molecules in the same sample at a given wavelength is directly proportional to the concentration of the substance in the sample. Absorption spectra are mostly determined in solutions. Emission and absorption values can nowadays be measured by modern spectrophotometers. To identify a substance and determine its concentration, an unknown substance can be identified by focusing light of a particle wavelength on it and then studying the absorption spectrum of the substance. Since substances absorb light only from a particular wavelength or wavelength range, the wavelength of light focused on them is important. This spectrum can be compared with a set of reference values for identification. These reference values are known absorbance values of common elements and compounds. The concentration of a substance in the sample can also be determined. And this is a photo of a spectrophotometer, which is a UV visible spectrophotometer. And this is the sample load unit that we put the test tubes, actually we call them QS, test QS, on the tray. And here is the control unit of spectrophotometer, which we can set the experiment conditions such as wavelengths. And this picture shows the basic structure of spectrophotometers. And we have a light source and a wavelength selector and the prism. And the wavelength selector provides us to select the wavelength that we want to send it to the solution. And at the other side of the solution, there is a detector. So there is an incident line in the solution and the transmitted line. And the detector determines the absorption and gives us the data. And this is the end of topic. And here are some references that I use in preparing this document. and also you can read them for further knowledge. There are both Turkish and English references. The next topic is solutions. And for biochemistry, clinical biochemistry, and more about the laboratory world, you may visit my website, biokimya.vet, and also you can subscribe to BiyokimyaVET Instagram channel. And please don't forget to subscribe, click on thumbs up, and open notification for further news. See you in our next topic. Goodbye.